Hello everyone. I hope all of you are doing well. Let us discuss today about elimination reaction, which is also known as beta elimination reaction. It is one of the reaction of haloalkanes in presence of a base, say alcoholic KOH. We have seen that alkyl halides, when reacted with aqueous KOH, they give substitution reaction. Nucleophilic substitution reaction takes place here. And the product that we get is a nucleophilic substituted product. In presence of KOH, the product is alcohol. It is alcohol. Now, this alkyl halide, when it is subjected to alcoholic KOH, then alcoholic KOH acts as a base and we are supposed to get alkene as the major product. Now, it does not mean that in case of aqueous KOH, we will not get alkene along with the alcohol. We will get, but alcohol will be the major product when we use aqueous KOH. But in presence of alcoholic KOH, alkene will be the major product. Now the question arises, why is it so? See, how do we define a base, especially a Lewis base? When we say Lewis base, we say lone pair holders are Lewis bases, and especially we will say lone pair donors are Lewis bases. How did we define a nucleophile? When we defined a nucleophile, we had said they are also lone pair holders or maybe a negative charge is there. That means electron excess species are nucleophiles. Now, since bases are also electron excess and they are having lone pair which is capable of donation, nucleophile is also having a lone pair. So any species having a lone pair or behaving as a nucleophile can also act as a base. When a species acts as a base, it gives elimination product as the major product. It gives elimination product as the major product. And when a species acts as a beta nucleophile, then it gives substituted product as the major product. So the example that we had seen with alkyl halide, when treated with aqueous KOH, we'll say that the polar medium, water, it actually helps in the generation of OH minus. So we get ROH, alcohol, as the major product along with the alkene. And when we treat this with alcoholic KOH, the medium is alcoholic and it acts as a base, and so alcoholic KOH acting as a base and it produces alkene as the major product. Now let us see in details what we have just now discussed. In case of beta elimination, let us cite an example of it. Say alkyl halide CH3CH2X. This is an example of alkyl halide. To this compound, when we give alcoholic KOH, and alcoholic KOH just now we have seen it is acting as a base, beta elimination reaction takes place, where from the beta carbon, hydrogen is eliminated and from the alpha carbon, halogen is eliminated. And why is it so? How is it happening? Just because the carbon having halogen bond is a polar covalent bond, developing a partial negative charge over halogen and partial positive charge over carbon, it induces polarity in the carbon-carbon bond which is next to it. For that reason, whichever hydrogen is attached to those carbon atom, if this carbon is having halogen, the one which I have marked with delta positive, then this is having the functional group halogen, and so this is alpha carbon. Any carbon which is directly attached to this alpha carbon is a beta carbon. And on account of the polarity of the CX bond in alpha carbon, there a polarity is induced in between the beta carbon and the alpha carbon, for which the hydrogen atoms which are attached to the beta carbon, they are acidic in nature. Citing an example of it, just like the one we had seen, say 3 carbon atom I am taking, CH3, CH2 and a CH2X in presence of a base, and I am writing it as OH minus. This OH minus, when I am writing, it is acting as a base. Now the hydrogen, I am just erasing one hydrogen. The reason is I want to introduce the hydrogen over here. So this is the alpha carbon and this is the beta carbon, where we have two acidic hydrogen. If the base that we have chosen takes the acidic hydrogen, I've given the dot because just a few seconds back or maybe few minutes back, we have just discussed that Lewis bases are lone pair holders. So just an assumption that maybe it's a Lewis base, or it can be, see, OH minus is also acting as a base. So whichever base you are taking, the base abstracts the acidic proton and this bond forms a double bond between alpha and beta carbon, and X is released as X minus. So let us again repeat the step what I said. The base that we have chosen, this is your base that we have chosen. This abstracts the acidic hydrogen, and we have two acidic hydrogen over here. This is one acidic hydrogen and this is another acidic hydrogen. That will abstract the acidic hydrogen. There will be a formation of a double bond between alpha and beta, and X will be released as X minus. So let us see the major product. The major product is CH3, CH, because out of 2H, 1H is given out or it is abstracted by the base. There is a double bond between alpha beta and CH2. So the alkene will be alpha beta unsaturated alkene. So this will be your major product. That means the elimination product is the major product. So what will be the minor product? Minor product is the substitution product. And what is it? It is CH3, CH2, CH2OH. This is the substitution product and this is your minor product. Now the question arises, if I have more than one beta hydrogen, like here we had more than one beta hydrogen, but both the hydrogen were of same type. These two hydrogen were of similar type. In this case, either of them can be released. But suppose we have two different types of beta hydrogen, then we are going to get how many product? For this I will say, please remember, as many types of beta hydrogen, as many types. Now here I will say to mark the term types. As many types of beta hydrogen, that many products we will get. That many products we will get. Now the question arises, okay, fine, we are getting many product. Now how do we know which is the major product? The most substituted alkene is the major product. So the most substituted alkene is the major product. And next the question arises, how do we know which is the most substituted alkene? Now the most substituted alkene will be the one having less number of hydrogen atom in the C double bonded C system. It contains less number of hydrogen atom in the C double bonded C system. This is as per a rule which is known as Saytzeff's rule. Saytzeff's rule. Now, some of the book may give you the term Saytzeff. So, you can use either of them. I generally use the terms, the name Saytzeff in this manner only. So, as per Saytzeff's rule, the most substituted alkene is the major product. This is the rule which I have marked. The most substituted alkene is the major product. So, just now we said that if there are more than one type of beta hydrogen, so as many types of beta hydrogen, that many products will be obtained. So let us see that. Suppose this is carbon halogen and this is a beta, and next to it there is another carbon, and here there is another carbon. That means that both the sides of CX, left hand side and right hand side, they are not identical, they are different. So now we fill it up. CH3, CH2, CH, and here a CH3. This is the compound. To this we have given alcoholic KOH. Obviously it is acting as a base. So let us see how many types of beta hydrogen are there. That is our first work. If CX bond we see and the carbon that is having halogen is alpha, then this is your beta carbon and this is also your beta carbon, but both are not identical. So if I consider one to be beta 1, the other will be beta 2. So the types of beta hydrogen are one from beta 1 and the other from beta 2. I hope you identified. See, beta 1 carbon having 3 hydrogen, that is one type. Beta 2 carbon having 2 hydrogen, that is another type. So now let us see. These are the types. This is one and this is the other. Now let us see how we can draw the products. Removal of hydrogen from beta 1. Removal of hydrogen from beta 1 and halogen from alpha will create a double bond between beta 1 and alpha. So the product will be CH3, CH2, CH, double bonded CH2. This is one product. The other product will be removing halogen from alpha and hydrogen from beta 2. So we will get CH3, CH, double bond, CH and a CH3. So since there were two types of hydrogen, beta hydrogen, we got two products. Now the question arises, out of these two products, which is the major product? For that, we have to focus on the C double bonded C system. This is the system in carbon compound 1 and this is the system in compound 2. So in C double bonded C system, here we can see in total there are 3 hydrogen, and here we can see in total there are 2 hydrogen in the system. So this is the most substituted alkene, and that's why this is our major product. I hope Saytzeff's rule, beta elimination and its application is quite clear. Now, the question arises that if I use aqueous KOH in RX, we have seen this, again I am giving for a reason. If I give aqueous KOH, then this is acting as a good nucleophile. And it has certain basic character also. So actually, I may get the nucleophilic substituted product as the major product, but the alkene will also be obtained as the minor product. Now, out of the two mechanisms, SN1 and SN2, which one will be the most probable mechanism for this nucleophilic substituted product? For that, we need to see the structure of Rx. If we have a 1 degree, then less hindered substrate, 1 degree or maybe methyl. So I can say a less hindered substrate will actually give SN2 as the more probable mechanism. And a substrate that can produce a stable carbocation, say for a 3 degree, then in that case what will happen? Say for a 3 degree Rx, then in that case we will have SN1 as the more probable mechanism. Now for SN2, the reaction rate will be CH3X greater than 1 degree Rx greater than 2 degree Rx greater than 3 degree Rx, just because of steric reason. But for SN1, it will be 3 degree Rx greater than 2 degree Rx greater than 1 degree greater than CH3X or methyl. Now, for a 3 degree, more probable is SN1 mechanism, stable carbocation. For a 1 degree or methyl, the more probable mechanism is SN2 because it is less hindered. But for a 2 degree, you know that SN1 and SN2 are equally probable. So for a 2 degree alkyl halide, both the mechanisms SN1 and SN2 are equally probable, and elimination is also probable based on the structure. But if I take alcoholic KOH, then obviously elimination will be the major product. So this point I had to say a couple of times because this is very important to identify. So let us see the checklist, whether we know the following things or not. That is, all bases are nucleophiles and vice versa. Because bases were also having lone pair, which is capable of donation, nucleophile was also having. So there is a common platform. Since they are vice versa, they are having both the roles. So the next thing is, wherever we have elimination, we also have nucleophilic substitution taking place. So elimination product and nucleophilic substituted product, both are getting formed. Now it depends on the medium whether elimination product will be the major product or substitution product will be the major product. For elimination product to be the major product, alcoholic KOH is a favorable medium. For nucleophilic substitution product to be the major product, aqueous KOH is a more. Now the next part of our discussion is reaction with metals. Reaction with metals. That means alkyl halides or haloalkanes, they react with metals, active metals like sodium, they react with metals like magnesium. So in this reaction with metals, we are going to see the reaction of alkyl halide with magnesium, a very electropositive metal, in presence of dry ether medium. And in presence of dry ether medium, alkyl halide with magnesium produces RMgX, which is an organometallic compound known as Grignard reagent. It is an organometallic compound known as Grignard reagent. Now, there is a speciality about this reagent. This Grignard reagent has a beautiful speciality. What is that? See, in case of alkyl halide, there is a bond between carbon and halogen. Halogen is more electronegative, having a partial negative charge, for which the carbon end develops a partial positive charge. Now, in case of Grignard reagent, where there is a bond formation between carbon and magnesium being much more electropositive, so this magnesium has a delta positive charge and carbon end has a delta negative charge. So here we can visualize a change or inversion in the polarity of the carbon. And this phenomena is known as umpolang. It's known as umpolang. Now, what is that? It is inversion of polarity over carbon. Inversion of polarity over carbon is known as umpolang here. Now, the term umpolang is not that much important for you all to remember right now, but it is of course very important for you to realize the fact that there occurs an inversion of polarity over the carbon and why it occurs. Now, after this, I will say that you mark this point that Grignard reagent formation can take place by this method which I have just now shown you. But the important fact is the medium should be dry. In the formation of Grignard reagent, one important fact is the medium should be a dry ether medium. So this dry ether medium that we are seeing over here, why is it important? Because Grignard reagent is unstable and it is highly reactive and it reacts with any source of proton to give hydrocarbon. Any source of proton. It reacts with water for that reason. It reacts with alcohols. It reacts with amines. So Grignard reagent is unstable actually. It's highly reactive. So it reacts with any source of proton. So what will happen if there are traces of moisture during the preparation of Grignard? We want to see that. See, Grignard reagent over here, if moisture is there or any proton source is there, it can give its proton, and what will happen, this bond which is between carbon and magnesium being a polar bond now, developing a polarity over there on account of the electronegativity difference between the carbon and magnesium, the bond breaks in this manner. Suppose hydrogen attaches to this end and OH attaches to this end. So when it breaks up, the product that you are getting is RH, which is a hydrocarbon. So it is said that Grignard reagent with the sources of proton forms a hydrocarbon and MgOHX is the side product. That is the reason that Grignard should be prepared under anhydrous condition. Next we go to a reaction which is known as Wood's reaction. Now Wood's reaction is a reaction where 2 moles of alkyl halide, say I am writing 1 mole here and the other mole I am writing in this manner. 2 moles of alkyl halide reacts with 2 moles of sodium in dry ether medium, reacts with 2 moles of sodium in dry ether medium, and there occurs an elimination of, or rather I'll say a formation of NaX. So this 2 moles of NaX is the side product over here and it forms RR, which is a symmetrical alkane having even number of carbon atoms. Even number of carbon atoms. So actually Wood's reaction is applicable for formation of symmetrical alkanes with even number of carbon atoms. And here we can see 2 moles of NaX is precipitated in presence of dry ether. So the medium is dry ether and you get a good yield of a symmetrical alkane containing even number of carbon atoms. So a question arises that why you cannot prepare alkane with odd number of carbon atom using Wood's reaction. See, it is not that you cannot prepare, but Wood's reaction says 2 moles of the same alkyl halide reacts with sodium. Now, if you take different alkyl halide, then you will get a mixture of compound RR, R dash, R dash. Booth's reaction is always applicable for producing symmetrical alkane containing even number of carbon atom. Because 2 moles of the alkyl halide if you take containing n number of carbon atoms, suppose each alkyl halide have n number of carbon atoms, multiplied by 2 will always be an even number. So the product contains even number of carbon atoms. So for that reason, Booth's reaction is applicable for obtaining symmetrical alkane containing even number of carbon atoms.